Hello everyone, thank you for coming. Today I'm going to talk to you about higher order functions and functions ref. And first I want to introduce myself. This is my first time in Russia. I had an amazing welcome, so I'm really having a lot of fun. But for people that don't know me, I'm a software engineer at Bloomberg, and I live in London. This is the new building that was created for our company. And I also do C++ training, both internally inside the company and externally through video courses. I published a few, as you can see over here. I also started my C++ career as a hobbyist game developer, and I have a YouTube channel with video tutorials on how to create your own games. And right now, I'm more interested in standardization, so I'm participating in the committee. I'm going to talk to you about one of my proposals, and also writing weird posts about esoteric metaprogramming on my blog. And finally, I also do a lot of open source work. It's mostly library development, and also some of my games are available on my GitHub page. I travel a lot for conferences. This is, I think, the 21st time I'm giving a speech, which is quite a lot. And I'm one of those people that constantly monitor Stack Overflow to answer your questions, just because I like to see my reputation score go up. It's like a drug. OK, so today we're going to talk about high-order functions, what they are, and how we can use them to solve some of our problems. And then the second half of the talk will be about this proposal I have to the standards committee, which is function ref. It's a new utility that's useful when implementing high-order functions, and we're going to see how to use it and how it differs from, for example, a city function. Disclaimer, yesterday we had this BOF session about functional programming, but this is not a talk about functional programming. Like, I'm not trying to convert you to the functional lifestyle. I'm just going to show you how you can introduce some concepts from functional programming and some utilities in everyday uses of, in everyday coding. So basically, I'm going to show you some practical uses of higher order functions and how to slowly introduce them in your code base, no matter what your style is. And also, this is going to show you like a little bit of insight into the design and implementation of C++20 proposals, so give you an idea what goes behind it and what kind of things are going to be standardized. Cool. I also expect you to be somewhat familiar with Lambda expressions, templates, and more C++ features, but please do not hesitate to ask questions during the talk. High-order functions. So how many of you know what a high-order function is, or has an idea? OK, it's plenty. That's good. So if we go to Wikipedia, we can find this definition that says, in mathematics and computer science, a high-order function is a function that does at least one of the following. So it either takes one or more functions as arguments, or returns a function as its result. So any kind of function that takes another one or returns another one is considered a high-order function. This is kind of a broad definition, but anything that you can think of that is considered one of them. Basic examples, as you can see here, we have a function called call_twice. It is a template function. It takes some arbitrary function object f, and then we invoke f twice in the body. And then we can use this utility, for example, with a lambda printing out hello to a cdc out. And in this case, it's going to print out hello twice. So this is a very simple example of a higher order function. It is considered one because it's accepting a function as an argument, and then it's doing something with it. And as you can see, we're using a template parameter here to take the function object, but this is not the only way you can do it. You can use SCD function, function pointers, and we're going to see that in the second half of the talk. Right now, we're going to focus more on template parameters. Another example of the other kind of higher order functions is one that returns another one. So in this case, we have this greater than function. It takes a threshold, and then it creates a lambda inside the body that captures the threshold by value. And then this lambda will take a value and tell you whether this value is greater than the threshold or not. And in this case, we return this closure over here. And we use auto-return type so that we can deduce the type of the lambda. And one way we can use it, for example, is in conjunction with an std algorithm, for example, count_if. And we can say count all the elements in the vector v that are greater than 5. So when we say greater than 5, here we're basically creating this closure, putting it inside the algorithm, and it's going to give us our answer, which is 2. So in this case, this is another higher order function. We are not accepting a function, but we are returning one. And the implementation technique here is creating a closure with a lambda expression and using auto-return type to deduce the type of the function. So now that you know what a higher order function is, do you think we have any in the C++ standard? Can you name a few? Yeah? More? Like, what are the most common higher order functions in the C++ standard? There's a word starting with A. Sort? What is sort? Sort is an algorithm. So all the algorithm library, for example, is full of higher order functions. But that was kind of easy. So do we have any higher order function in the C standard? Loud. Qsort, yes. So Qsort is one of them. We have bsearch. And we actually have more. We have stuff like addExit, addQuickExit, which accept a handler that will be set in order to be invoked when you exit the program. And one of them, for example, is cdsignal, which is quite uncommon, but it's also a higher order function if we see the definition. So I chose that one because it's quite uncommon, but it still fits the bill, in my opinion. And what it does is basically a function that takes an int signal and then some handler, which doesn't have a real concrete type. And it says that when the signal is raised, it will invoke the handler for you. So the handler, if you see the documentation CPP reference, says that it must be one of the following things, some weird C macros, or a pointer to a function where the signature must be equivalent to the following, so something that takes an int and returns void. And if, for example, we use signal over here, you can see that we pass sigint as the signal we want to wait for. And then when the signal is raised, we will invoke this lambda expression over here that takes an int, which is the number of the signal, and we'll print out inside the body. So technically, this is undefined behavior because you can do only a few things in the body of a signal handler. But I just want to show you that even more uncommon things that you might not think of are considered higher order functions. And you can see this pattern quite a lot. Another thing I want to show you with this slide is that lambda expressions work really well with higher order functions, obviously. They are a very convenient way of creating closures that you pass to the higher order functions. And also, if you remember the definition of signal we just seen, it accepts a pointer to a function, and we are passing a lambda. So the way this works is that stateless closures, so lambdas that do not capture anything, are implicitly convertible to function pointers. And this is why we can use one with a steady signal. In C++, we have a bunch of stuff. As I mentioned, the most common examples of higher order functions are algorithm and numeric. They contain stuff like accumulate, countif, findif, and so on. We also have utilities like bind and bindFront, which return some function. So that's another example of higher order function of the second kind. And then even new things like handling tuples and variants with visit, apply, and invoke. Those can be considered higher order functions because you're passing in a visitor, you're passing in some kind of callable object that will do something on the algebraic data type you pass to it. Some examples of practical use. Who here has heard of the erase remove idiom? Anyone used it? So yeah, this is quite a common idiom, and what you do is basically allows you to remove all the elements that match a particular predicate in an efficient manner from a contiguous container. So as an example, imagine you're writing some sort of game or maybe simulation where you have entities that can be alive or dead, and then you want to remove all the dead entities at the end of the computation step. One way you could do it is by using the remove if algorithm that takes an iterator to the begin and the end of the range, and then a predicate. In this case, the predicate is a callable object, a closure. And the predicate says, please remove everything that is not active anymore, so everything that is dead. And then this will return an iterator that, used in conjunction with the erase algorithm on the vector, will basically move all the elements that are still alive to the beginning of the vector and then destroy all the others in an efficient way. So it's not going to shift everything in of n to the power of 2 fashion. It's going to do it very efficiently by swapping elements. Another example that's a little bit more interesting, more modern, if you want to put it that way, is pattern matching with variants. So imagine you have some sort of event handling system, and this event can either be a connection, disconnection, or art bit. And the way we can represent that in modern C++ is by using a CD variant. And you want to basically process these events. Maybe they're coming from a queue, from the network, and you want to match on the event type and do something different. So one way you could do this by kind of abusing lambdas is by using this overload function we've seen in the keynote yesterday. And you pass all the lambdas over here, which represent your branches of pattern matching. And then you use stdvisit on the overload that you just created with the event. And what's going to happen is, for example, if I process an event containing connect, then it will print out process connect, heartbeat, process heartbeat, and so on. So this is a way you can use lambdas to basically create a primitive version of pattern matching in C++, which can be quite useful when you're dealing with variants. And if you're more interested in this topic, I have a talk that I given 2 years ago, and you can find it on YouTube over here. So, any questions so far about higher order functions? Does everybody have an idea on what they are? Okay. What are the use cases? So I've identified a bunch of categories. I think they're really good for removing repetition from your code, inverting control flow, dealing with asynchronicity, and also doing some compile time metaprogramming. We're going to see some examples of everything. So avoiding repetition for me is very important. I sometimes go overboard with it, the dismay of my coworkers, but I think that any kind of repetition leads to bugs and maintenance overhead, especially when you need to keep two things in sync and you forget to update one and the other. And sometimes people are reluctant to remove repetition because it can be quite hard. But I'm going to show you that with higher order functions, even complicated patterns can be abstracted away quite easily. So a very basic example is, imagine you have some sort of test. In this case, for us, it was an integration test. We were testing our routing suite for microservices. And we had this code over here where we create some machines, and each machine needs to have a unique port so they don't conflict with each other. And we had this context over here, which is basically some helper object for our tests that provides unique data, in this case, ports. So we have 3 machines with unique ports. And as you can see, we are repeating this invocation of reserved port with localhost multiple times. Now, this is not a big deal, but if in the future we decide to change localhost to run this remotely, or we want to change the way we use the ports, then we will have to modify the code in every single place. So one way we can avoid this maintenance overhead with very low cost is to create some sort of local function over here. And we can do that by using a local Lambda. We capture everything by reference because it's not going to go outside of the scope. And then we can call this something like getPort. And inside this Lambda, we will have the reserved port call with the IP address. And then every time we use getPort, it will basically do that for us. And the benefit of this is that we can simply change the IP address in one place, and all the code will be updated. So this is a very simple example how you can remove repetitions by using lambdas. This is not strictly a higher-order function, but another example where higher-order function can actually help you remove complicated repetition is something like this. So this is a real use case I had. I was writing a UI system for a game I was working on. And I needed to basically have this hierarchy of widgets where every widget can have multiple sub-widgets. And I needed to basically do some things in steps. So I had a step to recalculate the focus of every visible child, a step to recalculate the bounds of every visible child, and then a step to update all the children. And I had to do that in order because the focus affected the bounds affected the update, and so on. So I needed to do that in order. As you can see, the structure of this code is very similar in every for loop. We go through the children, we check that they're visible, and then we do some action on them. So how can we extract this code without creating a lot of boilerplate? Again, one way of doing that is, for example, creating a function with a lambda, so a local function, give it a very meaningful name, like for visible children. And in this case, this function over here will take another function f, which is our action that we want to invoke on the visible children. And then we put the control flow in the body of the function, and we iterate over the children, we check if they're visible, and then on each visible one, we simply perform our action on them. So now the main logic of our program is very clear. We simply say, for visible children, do this thing. For visible children, do this other thing, and so on. So we avoid repeating the control flow. We might change it in the future. And we simply extract the business logic, removing all the craft from the way we basically do the invocation. Another use case I have for higher order function is inversion of control flow. I think this is very important. And the idea is that instead of having some sort of control flow in your business logic, as we've seen before, what you do is you pass an action or a predicate to something that provides the control flow, and then you basically separate what happens from how it happens. I think one prime example of this in the standard library is the C++17 parallel algorithms. We've seen them as well in the keynote. But I really like this example because they completely changed the way the algorithm executed, but you still provide just an action, and then all the details on how this is executed, depending on threading model, or if you have a GPU or whatever, is abstracted away from you, and you just decide what to do and not how to do it. So a realistic example of this is maybe you might have some sort of physics simulation where each particle or object has position, velocity, and acceleration. And on each tick of your simulation, you want to basically compute the new variables. So you're going to add the acceleration to the velocity and the velocity to the position. And now, this is just your business logic. It's just this function that you're passing to the for each algorithm. And then the for each algorithm with a parallel execution policy is going to decide how this thing is executed. So all the control flow is inside the for each algorithm. What you do with the higher order function is you just provide the action you want to execute, which provides a clear separation of concerns and helps your code being more readable and also more testable. So the idea here is that we want to decouple the control flow from the desired action. And as I mentioned, you can test them separately. So you can test your action without complicated control flow, or you can test your complicated without control flow with a simple action. So you don't have to deal with complicated cases when writing unit tests. And obviously, they are also prone to reuse. Another example of this is printing a comma-separated list of elements. This comes up quite often. And the first solution I had for this is I assumed I have a vector of t elements that can be printed out. And I basically want to print out to SCDC out all the elements with a comma and a space after the comma without having any trailing comma or anything like that. So the algorithm goes as follows. I check if the vector is empty. If it is, I just return because I don't want to print anything. Otherwise, I print out the first element. And then I start from the second element up to the end, and I print out a comma and the element that needs to be visible in the output. So this is a very simple algorithm, and the problem here is that it only works with vectors, and it doesn't support, for example, customizing the printing action or the separation action. So what I do in these cases is I try to identify the structure of the algorithm. In this particular case, I have this action over here that is repeated both for the first element and also for all the other elements. And then I have this separation over here, which is, in the real case, putting a comma in there, but it could be something else. So after I identify the structure, I think, how can I abstract it this way? How can I provide customization points for the user? And in that case, this is where higher order function helped me, because I can provide them as callable objects that the user passes inside the function. So after I identify the structure, I create an abstraction. In this case, I call it for separated. It's not the best name, but I mean, it expresses iteration and separation, so it kind of works. And then my action becomes a function over here, and my separation becomes another function. So what I can do now is I have the same structure of the algorithms, but instead of printing, I just call the action on the element. Instead of putting a comma, I just call the separation, and then again, I call the action. So now I can use this abstraction to redefine my print in a simpler way. So my business logic now becomes just some lambdas in a customization point for separated. So my print is now just a call to the algorithm that passes the printing as the action and printing out a comma as the separation. And now the benefit is that I have this reusable for separated algorithm, which can be used for other kind of things and also tested more easily, because we are decoupling the printing from the algorithm. And the idea is that the user provides the action and the algorithm provides the control flow. So that's what I mean by inversion of control flow. An example of where this is useful is if you want to change the way you print something, maybe you're writing some sort of console application and you want some text to be more emphasized, then you might write something like white print that prints out every element separated by a space. And the way you can do it is by simply reusing the for separated algorithm with some sentence, and then you print out each character and a space between each character. And then when you call it with the white print algorithm, you're going to see some output like this, where there is a space between each character. So you can be more creative. You can use this for serializing stuff in a particular format, use dashes instead of commas and stuff like that. But the idea is that by using higher order functions, you can literally do anything you want, even have stateful separators that change over time, or keeping track of how many elements you're printing and so on. Any questions so far? Okay. This is another example that we had in production code. So we were working on this application where it's basically a broker for distributed systems. And we often had this use case where we had a set of systems that had to be initialized. And then we did some initialization pass. And then we moved all the ones that succeeded from a set to another set. So the way we call this function is by saying consume if with our set of systems. And you can imagine systems are either machines in a network or something like that, like nodes. And then we have our predicate, which is check if the system is initialized. And if it is initialized, then change its state to ready to synchronize and remove it from the set. So the idea is that we want to filter out things that have a certain predicate and also remove them from the set if they match. It's kind of a sweeping pass. And the way we implemented this is by having this consume if higher order function that takes a range, a predicate, and an action. And then we go through the range with a classical for loop with iterators. We check the predicate, and if the predicate matches, then we invoke our action on the object and consume it by erasing it from the set. And if you have seen this before, maps and sets, when you call erase, they give you back an iterator to the next valid position, so we fix the iterator. Otherwise, if the predicate was false, we just continue going. So before we had this kind of structure 2 or 3 times in the code, and it's really easy to make a mistake with, for example, forgetting to use the return value of arrays or forgetting to have the ++it in the else case. So extracting this to an algorithm makes it very easy to reuse and avoid mistakes, and also test this independently. OK, so that's inversion control flow. Another use case that I have for higher order function, which I think is really useful, is asynchronicity. So currently in the language, the easiest way to express asynchronous callbacks is using stuff like future, thread, and attaching continuations with lambdas. So if you have future, then you would want to have some sort of closure object, then you can do .then or when all and stuff like that. And the only easy way of doing that is with lambdas. However, there are some use cases that in the future might be superseded by language features such as coroutines, which are very likely to be in C++20. So this is another example of one other of my talks. It is about creating future composition without allocation or type erasure. So basically expression templates for futures. And what I did in this case is I had some nodes like the all node and the then node. And what the user provides is a bunch of functions and composes them together to create a graph of asynchronous computations. And then the user can just run the graph and everything will be done in parallel where possible and then provide the results automatically. So in this case, you can imagine I have this all node that takes 2 functions. And there are 2 long-running HTTP GET requests. So we want to do them in parallel. And then we attach a .then continuation that says, OK, when both are done, then aggregate the results in this payload tuple that contains the data of all requests. And then you can apply some sort of image stitching or something like that to produce the final result. So the point that I want to make with this slide is that higher order functions are currently the easiest way of expressing this kind of asynchronous graphs. There is no easy way in the language of doing that in a different manner. And finally, the last use case I find very useful for higher order functions is dealing with metaprogramming. So there are initiatives in the language in the standardization to make metaprogramming more imperative. Stuff like for ... for example, which would be a for loop over a tuple. Those are coming in 20. But before that, there really is no way of having imperative logic for compile time algorithms. So for example, if you want to have a for loop over a bunch of types, you need to do something that's a little bit more clever. I have a bunch of articles on this, but the idea is that by using higher order functions that are templatized, like template lambdas, you can create compile time algorithms such as enumerate types. And in this case, by enumerate, I mean the kind of enumerate you find in Python, so attaching an index to an element and then iterating over that. And then, for example, you can pass int, float, and char as your types, and then provide a closure, which is a C++20 template lambda. So if you've never seen this syntax over here, it's basically a new syntax in C++20 that allows you to provide template arguments to your lambda. And this lambda here will be invoked with 0 and int, 1 and float, 2 and char by this algorithm. And then inside of the body, you can provide your code that wants to be generated for each type inside of the list. And this is a very imperative way of dealing with types at compile time. And the only way I can find to, I can implement this in the language right now is by using higher order functions. OK. Another thing that I find very interesting and that I haven't seen before is comparing higher order functions to other abstractions that can be used to achieve the same goals. There are plenty of things that you can do both with higher order function and also stuff like RAI guards or iterators. And I was interested in seeing which one is better and what are the pros and cons. So this idea was sparked by some conversation I had at work about creating a very simple thread-safe wrapper over an object. So imagine that you have a bunch of data that you want to be sure is accessed through a mutex, so you want it to always be locked. One thing you could do is simply provide a mutex and tell the user, make sure to lock this mutex before accessing its data members, but that's error-prone because you can forget to lock the mutex. So what we do is have this kind of thing called synchronize of T, where you provide some T object, and then synchronized attaches a mutex to the T object, and every time you want to access the underlying T, you are forced to go through the synchronized interface, which ensures that you have the mutex locked. So for example, you have a class foo, which contains a bunch of data structures, and then you have the synchronized foo as foo that prevents you from accessing the underlying foo object unless you take the mutex. So what we want to do is provide some interface to the user that allows access to the underlying foo in a thread-safe manner. So there are two things we could do. We could use array guards, so something that you call maybe .access, and it gives you back some guard that locks and unlocks on construction and destruction, or a higher order function that where you provide an action, and the action is going to be executed under the lock for the user. So this is what it will look like in both cases. So in the first one, imagine we have this sfoo object, and then we want to access the underlying foo instance. So we can provide this interface where we call .access on the synchronized foo. We get back this guard f, and the guard will lock the mutex for you on construction, give you access to the object with the arrow operator or star operator, and then on destruction, it will unlock the mutex. So the benefit of this is that it ensures that the access to the underlying foo is guaranteed to be thread safe, and also it is friendly to control flow, as you can use this inside of a function, return when you have the lock, break, continue, and stuff like that. So this is a very simple way of achieving what we want. Another alternative is using a higher order function. So in this case, we can have a .access function on the synchronized wrapper, and then we provide the wrapper with an action. And this action takes a foo ref, so as you can see, it's the underlying type. And inside the body of this lambda, we have the logic that we want to perform on our object. So this again works because when we call access, we lock the mutex, we execute the action, and then unlock the mutex. So it guarantees thread-safe access. And the benefit I've seen that this is a very, very simple implementation compared to the thing on the left-hand side. However, as soon as you want to access the state that's surrounding the synchronized object, then you might want to capture things into the lambda. And if you want to return, like have an early return, you cannot do it because if you call return inside the body of the lambda, you would just return from the lambda. It is more complicated when you have loops as well. You cannot continue or skip iterations or break because you're inside the scope of the lambda. So it's not as friendly to control flow as the other one. So my main point here is that the higher order function is way simpler to implement, but it has some drawbacks in terms of flexibility. If we want to implement the guard synchronized, then what you have to do is basically create a struct over here, access guard. It will contain a lock guard and some operators to access the underlying T. You might want some constructors, maybe delete move, delete copy, make it a little bit safer. And then what you do with the access is just return it and provide access to the user to the underlying object. So it's not exactly complicated to implement, but there is a fair amount of boilerplate and things that you need to consider. However, on the case of the higher order function, it's literally a 2 lines function, and it's very, very easy to understand and review. So what you can do is simply provide access. Access takes an action f. Then we lock the mutex with this guard, and we call f on the object, and that's it. So this is the main pro and con that I see, is basically implementation simplicity versus flexibility. This also stands true for other examples, as example of like benchmarking a function. So anything that you can do inside of a scope can both be implemented with an array guard and a function object. For example, this is a benchmark high order function. It takes some action, and then it uses the chrono library to take the time between before the invocation, after the invocation of f. This is not the most statistically sound way of benchmarking, obviously, but it is simple enough if you need something quick. And again, you could implement this by returning some sort of guard that takes the time on construction and then computes the final result on destruction. So it's 2 ways you can do the same thing. Another example is against iterators or ranges, those kind of things. Again, you have the choice of using either higher order functions or iterators. As an example here, let's try to see how we can iterate over a filtered range. So we provide a predicate to filter a range, and then we want to iterate only on the elements that match the predicate. So one way we could do that with iterators is by providing some sort of filtered function that takes a range and a predicate and then exposes a begin and end. And then we would have to implement some sort of iterator that skips over the filtered elements. In that way, we can use it with a range-based for loop and achieve our result. So this technique, again, is friendly to control flow. You can use return, break, continue, whatever you want. It's more composable with existing algorithms because you can, stack iterators together and achieve your final, a more complicated way of iterating over this range. However, the implementation is fairly complicated. On the other hand, if we use some sort of for-filtered high-order function where we provide a range, a predicate, and a lambda to execute on every element that does match the predicate, then we can achieve the same result by providing our logic in the body. The implementation is going to be way, way simpler. However, again, we have the problem of requiring captures and being unfriendly to control flow, like return, break, and continue. So again, to show you the implementation, if you want to do something like a filter iterator and do it properly, make it compatible with the rest of the algorithms, then it is not trivial anymore. Like you would have to write something like boost iterator, so make sure you have all the right traits, all the right constructors, you expose the right interface for the iterator, and so on. And this could potentially also be slower than the higher order function, depending on your optimization level and how you implement it. So this is not a trivial task anymore, and you need someone that's experienced in library development to do this properly. However, for full filtered, is literally three lines of code. So what you do, you provide a range-based for loop, a if check, and then call the action if the predicate matches. So again, our technique here is simply passing the predicate as an action and high order functions, and that's it. So you can see that there is a very big difference in implementation complexity and flexibility of these utilities. My main takeaway from this is if you're developing something that you expect to be used from a lot of people, maybe a utility for your team or utility for your company, then take the time to do it properly with either AI guards or iterators. But if you need something that makes your business logic easier to understand and is not meant to be reused, then it might be worthwhile having a simple implementation with higher order functions that might be less flexible but easier to review and understand for your colleagues. There are some changes like in 17 and 20 that make higher order functions more powerful. For example, we have context per lambda in 17 or template lambdas in 20. There have been some proposals that might have helped to make this even nicer, like more ters lambdas. But in general, these are the takeaways you need to get. One is more complicated than the other, and it depends honestly on the way you're using them and expecting other people to consume your utilities. And also, if we have alternatives such as coroutines and ranges in the future, it might change the way you solve these problems. OK, so that was the first half of the talk. Now let's get into function ref. What I'm going to talk about is basically this new proposal that I have in the standard committee. It's probably going to make into 20, worst case scenario into 23. And it's a simple utility that allows us to implement higher order functions in a different way compared to templates. So I want to see what options do we have right now in the language to implement higher order functions. So what can we do? One of the most basic options that's also available in C is pointers to function. So imagine maybe you're writing some sort of calculator where you want to take an operation f and perform that operation onto numbers like 1 and 2. So maybe this could be addition, subtraction, multiplication, whatever. So how do you allow these operation functions to accept the arithmetic operator that you want? One way you could do this is by a pointer to a function. We call this function pointer f. It takes two integers and returns an int. And then we can provide our action. This is a valid higher order function. However, it has a bunch of drawbacks. So it doesn't work with non-member function and stateless closures. So if you have some sort of lambda that captures anything, then you cannot use it with a pointer to member function because the conversion doesn't work. If you have a member function, you cannot use it here as well because a member function pointer is different from a function pointer as it requires to know what the object is. And also, it doesn't work with stateful callable objects. So maybe if you have a struct that has an overloaded operator call and you have some state inside the struct, then you cannot use it with this operation implementation. However, it has two very big advantages, which are it has a very small runtime overhead, and if everything is in the same transaction unit, then the compiler can just inline everything and make it as if you had written the function inline. And it's also constrained with an obvious signature. So you've seen in the previous slides, and when we were accepting template parameters like f or f actions, we don't really see the signature of the function as part of the code. However, here we see exactly that it takes two integers and returns an int. So that makes the errors better if you screw up your signatures, and it also makes it easier to read what the code is supposed to do. So the second options that we explored in the first half of this talk is template parameters. And what we do here is basically provide our action as some template parameter f. We take it by forwarding reference here to accept any value category, so temporaries, non-temporaries, even mutable lambdas that are temporaries, and so on. And we basically invoke this inside the body, either by forwarding or not, depending on what you want to do. Now, as you can see here, we have a huge benefit, which is flexibility. This works with literally any function object, or even callables, which include pointer member functions if you use std invoke. It is basically a zero-cost abstraction. This is required to be defined in the header. The compiler has all the information it needs to inline all the code and make it as optimized as possible. And this is the reason why standard algorithms use templates, because they want to basically disappear as much as possible thanks to inlining. However, before C++20, this is hard to constrain. So if you want to provide a meaningful error message to your user or restrict the domain of this function, then you would have to use spinning with the enable if, and is invocable and stuff like that, which doesn't make the code nice to read, and it's a technique that's more difficult for new hires and people that are new to the language. In 20, however, we have concepts, so this bullet point might be invalid. You might just be able to say a nice concept, and it would just look nice and work properly. And one important point, especially for companies like Bloomberg that have huge code bases, is that it might degrade compilation time. So sometimes we'd rather have a hit at runtime performance in order to make our compilation times faster. It is a reasonable trade-off, and if we use template parameters, we are forced to define these things in the header, and we are forced to take a compilation time hit. So that's one possible drawback. Oops. Then we have a std function that everyone loves too much, in my opinion. And what a std function is basically a polymorphic wrapper over any callable object with a given signature. So it's not exactly lightweight. It's not exactly, some people think they are related to lambdas or stuff like that. No, it's just a polymorphic wrapper over some callable with a given signature. And the way you use it is simply by accepting this function and then invoking it like it was a normal callable object. This implementation is fine because it works with any function object or callable. It has, however, significant runtime overhead. It is hard for the compiler to inline and optimize the std function at the time of this talk. Maybe in the future things will change. But the problem here is that the std function has a bunch of features like small buffer optimization. It can allocate. It always owns the callable. So it makes it hard for the compiler to reason about it and inline everything. Another good thing, it is constrained with a very obvious signature. You can see the signature right there. Takes two integers and returns another one. And one other, maybe this is kind of a stretch, but it also can have unclear semantics, depending on whether you initialize it with a function or maybe a reference wrapper. Then you can have either reference semantics or running semantics. Again, this is not a major issue, but it would be nice if we had certainty about what this thing is doing by just simply looking at the signature. And then finally, we have my proposals is function ref, and what this does is a very lightweight view over a callable. And as you can see, the syntax is exactly the same as a std function. You provide your function ref, takes two integers and one int, and you invoke it normally. And as you can see here, I'm taking it by value because it's extremely cheap to copy. So this works with any function object or callable. It has very, very small runtime overhead. This is exactly the same as function pointers. So if everything is in the same TU, the same translation unit, everything will be inlined. It has a constrained and obvious signature, and it has clear non-owning semantics. So if you see function ref, you know exactly this thing doesn't own anything, it's just referring to an existing callable. And the way I like to think about it is think about string view but for functions. It's the same principle. It's just a lightweight view. It doesn't extend the lifetime. It doesn't own a callable, but it provides you an easy way of referring to it. So it comes with all the advantages of Street View, but also all the disadvantages. And we're going to take a look. In general, function ref takes a signature with a return type and a bunch of arguments, and that's a non-owning reference to a callable with that signature. The parallel that I mentioned is, if you think about string to string view, you think about function to function ref. It's the exact same thing. So string view is a reference to a string. Function ref is a reference to a function. It doesn't own or extend the lifetime of the reference callable. So it's very easy to get into situations where you have dangling references if you're not careful with this. Exactly the same as string view. But it is lightweight, friendly to no-accept and optimization. So most of the interface is no-accept. Most of the implementation is very simple so that the compiler can get rid of it. And it is currently going through standardization. It is being approved by the evolution group. So now we're just fixing the wording and refining the proposal. And many thanks to the people on the slide that helped a lot with writing the proposal. So why would you ever want to use function ref instead of std function? Because they're very similar. The main reason that I see for this is performance. You can usually get way better performance with function ref and still maintain your compile time at a fast speed, because you don't have to define this in the header. Also, the clear reference semantics are important in some projects. Like, you want to make sure that people understand that you want to accept a reference to a callable, not own one. So having function ref as part of your type signature makes it clear what your intent is. And the other question I might ask, why would I want to use function ref instead of template parameters? Template parameters have the same performance, but they have some drawbacks. First of all, template parameters are harder to write, read, and teach, while function ref is very easy for people to get used to. Function ref is usable in polymorphic hierarchies. So if you have like a virtual function that takes a function ref, then you can override it, while you cannot do that with templates. You can use type erasing techniques, but then you're back to a std function, so it doesn't really help. And then better compilation times and physical independency of files. So that's another major advantage, especially for big companies like Bloomberg. We want to make sure that we have a less coupling at compile time as possible, because we have code bases that are too big. So this is what it looks like in the interface. You basically have a void star object that refers to any callable object, and then an erased function pointer that allows you to invoke the operator call or the function that you are basically referring through the object pointer. And then you can construct this thing. You can construct it from any callable f. There is some magic here to make sure that f matches the signature you passed. You can assign it. You can rebind it to another function. You can swap it, and you can invoke it. So that's pretty much it. It's very simple. Here are some use case examples. This, again, is the same project, the broker project that I mentioned before at Bloomberg. And what we did here was basically, we wanted to support replaying of the packets in the network in the same way they came in order to simulate production data and test on that. And the way we did it is by basically have two maps, one that mapped a command ID to a ref-counted command, as these commands have state and they can be quite expensive. So in order to save memory, we wanted them to be ref-counted. And then we had queues, which you can imagine is all the commands that a user did, so binding a user to a set of commands with a deck. And then what we want to do is basically provide a way, I give you a QID, so a user, and I want to replay all the commands of that user. How do I present this in an interface that's easy to use and hard to misuse? So we had experimented with returning an iterator or providing some begin and end, stuff like that, but it is quite tricky to both implement and ensure it's used properly. So what we ended up doing is use function ref over here, and we say, OK, we have this iterate function. You give us the QID and a function ref that processes the commands, and then we guarantee that every command is going to be processed as part of the function ref invocation. So the way it works is that we find the queue, and then we iterate over all the elements in reverse, because we want to simulate the exact order in which the user performs the command. And then we invoke the action with the elements from the queue. So it's very simple. It's not a complicated algorithm, but compared to the alternatives in which we can expose this interface to the user, function ref was the best alternative between template parameters, a std function, or iterators. So it's kind of in a sweet spot where you need something between function and template parameters. Another example here is with virtual hierarchies. So we had this concept of a packet cache. We wanted to cache some packets for speed and performance reasons. And each packet cache could support replaying, so what we've seen before, and also consuming. And as you can see, replaying implies that you can do this action multiple times. So you take an action that takes a packet by const reference, while consuming implies that you want to basically consume all the packets in the cache and clear it. So this takes the packets by R-value reference, which is faster, but also destroys them, basically. And the packet cache, we wanted to have multiple implementation that we could switch our runtime, like LRU, or a simple contiguous packet cache, testing cache, and so on. So we didn't want to have a viral template, have all the things that use packet cache also be templates. We want this to be polymorphic, so we wanted virtual voids. So again, the sweet spot between the SAD function, which is too expensive, and templates which don't work with polymorphic hierarchies, was function ref. So we use this replay and consume virtual function that take the function ref, and it worked quite well. So one basic implementation of this would be the contiguous packet cache. It overrides replay and consume. For replay, it just go through the packets and call the function ref. And for consume, it would just move the packets into the function ref call so that the caller can do something more dramatic with them, like put them in another place. And then we clear the cache after we finish consuming. So this is an example how you can provide interfaces that are quite flexible without having to write complicated iterators and making it obvious for the user what is going to happen. And also not paying the price of a city function or templates. This is the last one. I don't have that much time, so I'm going to go quite quickly on this. But the idea is that we have this node monitor. It keeps track of the health of nodes inside of a network. So this can be machines or whatever you want. And we wanted to sweep over this node monitor to see, to find all the machines that had timed out over a specific timestamp. And then all the machines that have timed out, we want to change their state from A to B with this callback over here. So in order to represent the state change, we again use function ref. And what we did was basically ask the user to give us a function that takes a node ID and a state transition, and we will apply that function on all the machines that match the timestamp threshold. So in this case, we iterate over the machines that are stored in some set or some map. We check the states, and we compute the last heartbeat of the machine, check it against the threshold and the current timestamp. And if the machine has timed out, then we invoke this action that the user provided. We pass the machine in, and we change the state to something, for example, to down. Again, if the machine goes down, we remove it from the set. We don't want to keep track of it anymore in the node monitor, and we keep going. So if you see this, and you remember the beginning of the talk, this is exactly the algorithm that we've seen before, is consume if. So this is one of the places where we use consume if. And this is what it looks like after abstracting a little bit more. So sweeping is consuming if the threshold is below the last heartbeat, and consuming means that we change the state and remove it from the original set. And again, function ref was really helpful here because we didn't want to have a compile time coupling of the node monitor with other components. We didn't want to make it a template, but still we didn't want to take the overhead of a city function. We wanted something in between. Okay, so now how do we implement this thing? So the first thing is creating this base class function ref that takes a signature and then specializing it on a return and the arguments. So you can do this to basically pattern match on the return type and the arguments of a signature. Then, as we've seen before, we're going to store a pointer to the callable object, which is PTR, and it's a void star because we don't know the type of the object in advance. And then we're going to store a function pointer that has the same return type as what we specified in the template, the same arguments of what we specified, but also takes an extra void star, which is going to be exactly the same as underscore PTR. So what we're going to do when we invoke function ref is pass the PTR pointer as the first argument of this erase function, and then the arguments provided by the user, and we're going to figure out how to invoke the original object. So this void star over here is the same as this one. So this is how it works. All the magic is basically in the constructor. We have this constructor that takes a callable object f. In reality, we would constrain this to match the signature, but here for simplicity, it's just unconstrained. Then what we do is we store the address of f inside this PTR object, which is a void star. And then we create this erase function, which is the other function pointer, by using a lambda that doesn't capture anything. And if you remember that, is going to be implicitly convertible to a function pointer. And the body of this lambda would just reinterpret cast the PTR argument to the original type f, which is available in this context because it's the template type of the constructor. So we do have f in this context. We reinterpret cast the PTR to f, and then we invoke it with the arguments over here. So all the magic is here. We basically are in a context where we know the original type of the callable. So we create this erase function where we remember what the original type of the callable is, and by accepting a void star, which is a type erase callable, inside this static lambda, then we can interpret cast it to the original type and get the behavior that we want. Make sense? A little bit dense, but this is a basic example of type erasure. And when we invoke, all we do is basically invoke erase function. We pass our pointer as the first argument, and this erase function will take care of reinterpret casting to the exact type that it was before. And then we provide the arguments that the user gave us, and you will get the invocation that we expect. So this is kind of the full implementation if you want to have a look. Full is obviously a lie. You need all the extra stuff like constraints, copying, swapping, and so on. But this is the basic idea. Just have an erase function, a void star pointer, set them up in a constructor, and go through the erase pointer inside the call operator. OK, so like string view, there are some pitfalls. So this thing is not safe to use unless you follow some guidelines. So as an example, who can tell me what happens here? Yeah, I heard it already, undefined behavior. Why is it undefined behavior? Well, we are using a function ref to store a temporary callable object created by a lambda. And what's happening is basically the lifetime of this object is only valid for this line. So on the second line, the lambda will be gone out of scope. It will be destroyed, and we are accessing the destroyed object by invoking the function ref. So you get the exact same problem with string view and strings. Is a limitation of the language when dealing with reference and view types. And unfortunately, unless we have something like Rust lifetimes, we cannot get rid of this behavior quite easily. There is work going towards that, but it is a pitfall of function ref. The bright side of this is that if you only use function ref as is intended use, which is basically accepting a function in a higher order function, then you never get into this problem. If you start doing more tricky things like storing function refs in places and putting them on the stack, then it's up to you to make sure that all the lifetimes match. So this is another example. This might be a little bit more surprising, but even if you take a free function, then even in this case, it will be undefined behavior, because what we're actually storing is a pointer to the free function, because that's considered callable for the language rules. So even doing this would be undefined behavior. Now, this is weird. You're saying it's a free function. Why would it ever be undefined behavior? We can make this work. Like, we could remove the second indirection by detecting it's a free function. But then we would be inconsistent with stuff like pointers to member functions, and the benefit wouldn't be as great. So I'm happy to discuss with you later. I don't have much time to go into the details, but we are aware of this problem. Unfortunately, there is no obvious best thing to do here. OK, so important part, benchmarks. I've been talking about the performance of this thing, but if I don't show you benchmark, what's the point? This is a very simple scenario. We will invoke a higher order function in a loop, and then we will test that same higher order function with a template parameter, function ref, and SCD function with and without inlining. And I'm using Simon's brand's function ref implementation. It's available on GitHub for free, and it's like a standard compliant implementation of function ref, and also using Google Benchmark through the QuickBench website, which is quite amazing. So this is what it looks like. I have a bunch of higher order functions. One takes a template parameter, one an SCD function, and one a function ref. And I'm using this benchmark do not optimize thing to prevent the compiler from seeing through the call and getting rid of everything. And then I'm just calling the function. And I also have no inline versions to see how inlining affects this behavior. And then what I simply do is iterate over the state, which is something that Google Benchmark provides, and call my higher order function. So this loop will go as long as Google Benchmark requires to in order to get an accurate measurement. Let's put it that way. So these are the results. if we have inlining enabled and everything is in the same translation unit, then both template parameters and function ref have exactly the same speed. So if everything is the same translation unit and if you have an inlining, then function ref is as free as a template parameter, but you don't get a compile time overhead. And now you can see the big difference. Inline function ref versus a CD function that is inlined is 7 times faster. So there is a huge performance boost in that case, which puts function ref in a sweet spot between template parameters and a CD function and applicable for certain use cases. If you don't have inlining enabled, then even template parameters is 3.5x slower than a normal inline version. However, you can still see that function ref and a CD function follow the same order. Function ref is 8 times slower than template parameter, but a CD function is 11 times slower. So even without inlining, there is still a significant benefit in using function ref. All the results are consistent. This is GCC 8.x. This is Clang, and this is Clang with libc++. And the hierarchy is always the same. You can always see that in every case, function ref and template parameters with inlining are the same, and function ref is always 7 times or 8 times faster than a CD function. So the conclusions are that when inlining happens, function ref is always as fast as a template parameter, and SCD function is at least 7 times slower than function ref. When inlining doesn't happen, then function ref is around 2 times slower than template parameter, and SCD function is 1.5x slower than function ref. So it's not as dramatic, but there is still a benefit there. The takeaway is that function ref is optimizer friendly and thrives with inlining, and is always faster than SCD function independently of your build cases. This was tested with full optimization level on the compilers that you've seen there. This might change in the future if they find ways to optimize function better or function ref better. And also, I haven't tested this, but my assumption is that with lower optimization level, function ref is going to have an even more dramatic performance boost over CD function because it avoids a lot of craft. So if you're like a game developer that likes doing a lot of debugging with low optimization level, or if you cannot compile your code with O3 or 2 for reasons including debugging and figuring out what is happening, then function ref would be a lot better than CD function in use cases. So conclusion. We've seen high-order functions in general are any functions accepting or returning another, and we have many examples in both the C and C++ standards. There are varied use cases, mostly avoiding repetition and inverted control flow, but also asynchronicity and metaprogramming, and they are highly usable thanks to Lambda expressions. We have ways to implement them. Basically, we have seen pointers member functions, function ref, CD function, and template parameters. They all have pros and cons, so you have to think about your use case to figure out what is good. And like if you want to take anything from this talk, you don't have to go fully functional to benefit from this kind of abstractions and ideas. So you can introduce them slowly in your code base and reap the benefits over time. Function ref is a non-owning reference to a callable with a given signature. It will hopefully be in C++ 20, worst case scenario 23. It is lightweight and trivial to compile to optimize, and it has clearer semantics and higher performance compared to a CD function. And you can start using it today. It's quite straightforward to implement if you look at the paper over here, or you can use this open source implementation from Simon Brand, which is compliant to the standard. Thanks, everybody. You can find me later. I don't know if we have time for questions.
So I'd like to address your slides where you accept the callable through universal reference.
Through what, sorry?
Through universal reference, like the template parameter with the
forwarding reference, right?
Yes.
Let me find one.
So in some examples, you use .forward before invoking the function, and in some examples, like for filtered, you don't.
Yes.
So do you have any advice on whether we should forward always or not?
Yes, that's a really good question. So remember that forward is nothing but a conditional move. And it basically means I will move if the thing originally was an R value, otherwise I will do nothing. So when you move a callable object, then you are in one way consuming it. So if that thing has an R value qualified call operator that maybe consumes a resource, then the idea is you can only do that once. So you should forward only once That's my takeaway. If it's something like this one, where I have an operation and I'm invoking it, I can forward because it's just calling once. If I'm calling it inside of a loop, then I don't want to forward because I might move the same callable object twice. To be completely pedantic, you will be able to forward on the last iteration of the loop, but that's a little bit, too pedantic, harder to implement, and is not really worth the benefit. But that's a really good question.
Thank you for the great talk.
Thank you.
You can continue in the discussion zone. Vittorio will be there in a couple of minutes.
Thank you.